This presentation is delivered by the Stanford Center for Professional Development.
Okay, like I said, I wish we had one additional day in this quarter because don't quite have enough time to do what I want to do in full detail, or even if not in full detail, and just somehow just enough detail so you can see some of the finer points of the arguments. But nevertheless, I still think it's a good idea to try to go over the main highlights of two more topics. One, a continuation of what we talked about last time, the general stretch theorem, and actually a sort of an application and a physical manifestation of the general stretch theorem. And then the last topic, which I'll begin today and then finish up next time, on medical imaging, an application of the two-dimensional Fourier transform to medical imaging. And again, I'm sorry, I really do regret not having one more day somehow that we could do this in a little bit more detail, but it'll give you at least a sense of some of the directions that some of this material goes. So today I want to talk about, and actually this harkens back both to yesterday, last time, and stuff we did earlier when we first started talking about the Shaw function. I want to talk about Shaws, lattices, and crystallography. Crystallography, okay? Now, I'm doing this because I really think this is a really interesting application. It's very pretty, and it just shows you somehow how some of these ideas come into play in unexpected ways. This is an application, although again, unfortunately, we can't see all the details. I just don't have time to give all the details, although it's discussed in the notes. This is an application and, say, physical manifestation of this idea that in higher dimensions, reciprocal means inverse transpose. All right, that's what we talked about. We talked about the general stretch theorem, and I'll remind you what that says. So physical manifestation, physical example. Manifestation is too long a word for a man with a grip. Physical example of the idea is reciprocal means inverse transpose. All right, now we saw that phrase, that aphorism, in the context of the generalized stretch theorem. So I'll remind you what that says. And that comes into the derivation of what I'm going to be doing. So we saw this in the generalized stretch theorem. Which told us how to take the Fourier transform when I make a change of variable by a matrix and not just scale the variables independently. So it said this. It said the Fourier transform of f of ax. All right, so you change the variables x by a matrix A, a non-singular matrix A, is 1 over the determinant of A times the Fourier transform of f evaluated at A inverse transpose at the frequency variable c. Okay? It's a very interesting looking formula. We derived it last time, and it's complicated. It's more complicated than the one-dimensional stretch case, but it includes the one-dimensional stretch case. But what you don't see in one dimensions is this new phenomenon, as I say, that reciprocal somehow means inverse transpose. And that's something new. That's something different on the scene. All right, so now I want to show you how this comes in these contexts. So first of all, I want to talk about how we might generalize the Shaw function to higher dimensions. So let me remind you of the Shaw function in one dimension and some of its main important properties. So I want to generalize the Shaw distribution. It's a sum of deltas. Sum of, let me say, evenly spaced deltas. All right. So in one dimension, we had the model case. That was the Shaw function with space, where the deltas are spaced by 1. So you put a delta at each integer point. The model case is the basic Shaw function, where you put a delta function at each integer. 1, 0, 1, 2, minus 1, minus 2, and so on. All right. And you define the Shaw as just the sum of those delta functions. Shaw of x is the sum k going from minus infinity to infinity at delta x minus k. So there's a delta function at each integer point. And the remarkable property, and as we said when we were talking about this, is the deepest property known about the integers. It's equivalent to this fact in number theory called the Poisson summation formula, is the Fourier transform of the Shaw function is itself. All right? The Fourier transform of Shaw is Shaw. And that was fundamental in a lot of the work we did. It was fundamental certainly to the sampling theorem and a lot of other applications. We actually looked at this and a slightly more general version, which I'll remind you of just now, in the context of crystallography, sort of as a way of motivating it. And I'm going to talk exactly about that in just a second. All right, so we generalize this slightly. We allow for spacing p. Spacing for other spacing other than the integers. So spacing p. That is to say, it doesn't matter what I call it. So instead of spaced at the integers, I put deltas at the point 0, p, 2p, and so on, minus p, minus 2p. All right, so this time the Shaw function is same sort of definition, but the spacing is different. So it's again the sum from minus infinity to infinity of delta x minus k times p. And here the fundamental result is that when you take the Fourier transform, the spacing becomes reciprocal. All right? That is the Fourier transform of the, let me use a subscript here, p, to indicate that that's what the spacing is. All right, sorry. The Fourier transform of the Shaw function with spacing p is actually two places where the reciprocal comes in. It gets scaled out in front by 1 over p, and then the spacing of the deltas in the frequency domain, the spacing of the deltas when you take the Fourier transform is spaced by 1 over p. All right, that's pretty cool. All right, it's a very interesting result. All right, and it's a very important example of this sort of reciprocity relationship between the two domains. All right, and this is what I want to generalize. All of these properties I want to generalize. Now, I'm going to stick in 2 dimensions, but really, and there's a change from 1 dimension to 2 dimensions, but there's very little change from 2 dimensions to higher dimensions. I can draw the pictures more easily in 2 dimensions. But really, to say all I have to say will hold in higher dimensions, in particular 3 dimensions, which is really the appropriate setting for studying crystals. But I'm going to, as I say, I'm going to, just so I can draw the pictures a little bit more easily, I'm going to write things and speak about things just in 2 dimensions. All right, so what's a generalization of Shaw? Let's say to 2D. All right, what should it be? Well, what I want to do is, there are 2 parts of the Shaw function. I put a bunch of delta functions, but before I put the delta functions down, I have to have a set of evenly spaced points. That was the whole idea behind the Shaw function. So you need, that's the first thing is you want evenly spaced points, and you have to decide what that means. Evenly spaced points in the plane, in R2. Okay? Now, there are a lot of different possibilities here, but again, we started with a Shaw function with a model case where the deltas, where the points were spaced 1 apart. So for my model of evenly spaced points in the plane, I'm going to take all the points in 2 dimensions whose coordinates are integers. All right? So I'll take a grid in the plane whose points have integer coordinates. All right? Like so. So that's going to be my model for evenly spaced points in the plane. And of course, the higher dimensions, it would be the similar sort of thing. I would take points with integer coordinates, in R3 or in higher dimensions. All right, so a point here, a grid point, has coordinates k1, k2, where k1 and k2 are integers. All right? All these points. And those points are said to form a lattice. All right, that's not an unfamiliar term. So this forms what's called the integer lattice. Integer lattice in the plane. And it's denoted by Z2, sort of a bold-faced letter Z. I can't remember if I've used that notation before, Z for the integers, to stand for the integers. Z stands for the German word Zahlen, which means number. All right, and it's a universally adopted term pretty much universally adopted term, certainly in mathematics and more and more so in engineering, just to denote, and applications, just to denote the integers. All right, so Z2 meaning it's in 2 dimensions. All right, so this is the set of all points, nothing but the set of all points, the lattice points in the plane with integer coordinates. And my Shaw function is going to be defined by putting a delta at each one of those points. Put a spike at each one of those points. So define Shaw by putting a delta at each one of those points. Each grid lattice, I'll call it lattice points, okay? That is, I'll define the Shaw function for this integer lattice, Z2. It's exactly the analog of the one-dimensional case of x. It's going to be the sum, let me write it like this, k in Z2 of delta x minus k. So again, what I'm trying to do here is I'm trying to make this look as much like the one-dimensional case as possible. So if I write the vector k, what I mean by that is it's a pair, k1, k2, where k1 and k2 are integers. So if I write it like that, again, it looks like the one-dimensional case. So here, again, k, it's just shorthand notation, k1, k2. Integers. Okay, now, all right, let's see here. The basic phenomenon, well, again, generalizing the one-dimensional case, is what happens to the Fourier transform of the Shaw function for the integer lattice. And this is, as I say, unfortunately something I don't really feel like I have the time to derive, and it just kills me, but I'll give you the result. So just as in the 1D case, you have that the Fourier transform, and for the same reasons really, it's a straightforward, you set things up so it looks exactly the same as in the one-dimensional case. You have the Fourier transform, the two-dimensional Fourier transform of this lattice, the Shaw function based on the integers is itself. All right, and the proof really, again, the derivation of that is the same as in the two-dimensional case, as in the one-dimensional case. It depends on higher dimensional Fourier series, but it's really very much the same. You can use the same words and really follow the same argument. The argument is very much the same. Very much like the 1D case. Okay, now, things get more interesting when you ask yourself, how do I change the spacing? All right, in the line, in one dimension, you only have 1 degree of freedom. The only way to change the spacing is to stretch or shrink in one direction. All right? So how do I change the spacing? Change the spacing for a 2D lattice. What should we mean by that? All right, we still want the points to be somehow evenly spaced, but not the same. All right, well, again, in 2 dimensions, we have more degrees of freedom than in 1 dimension. But for our purposes, there's a very natural way of looking at this. All right? In 2 dimensions, in 2D, we obtain a different lattice. Let me just say informally, let's just call it an oblique lattice. I'll draw a picture in just a second. That is, we change the spacing by applying a linear transformation, a 2x2 matrix, say A, to the integer lattice. All right, now that's what it is in words. Let me draw a picture so you see what I mean here, because it's not hard to see. Not hard to see what I mean. So here, let me draw a picture of the integer lattice. Over here. All right, so this is Z2. And a matter of fact, let me even let's consider this the origin, and let's take this to be the basis, the natural basis of R2. So the 2 natural basis vectors is 1, 0, and 0, 1. All right? Now I take a linear transformation, a 2 by 2 matrix A, non-singular, so nothing's getting collapsed. Then they're going to take those basis vectors E1 and E2 to some other vectors, say V1 and V2. All right? And they're going to take, now all the points in the integer lattice are just integer combinations of these basis vectors. If I want to reach the point 2 over here, then I just take 2 times E1. If I want to reach the point 2 up here, I take 2 times E2. If I want to reach this point, I take E1 plus E2. Okay, 1 times E1 plus 1 times E2 and so on and so on. So all the points in the integer lattice are just integer combinations of the basis vectors E1 and E2. Under a matrix, a linear transformation, they go over to integer linear combinations of V1 and V2. So what I have over here is a picture that looks like this, where the lattice points over here correspond exactly to the lattice points over here. And so on and so on. Okay? So the lattice is sheared, if you want to think of it that way. The square lattice of the integers is made into an oblique lattice by taking a matrix that takes the basis vectors over here, the natural basis vectors, and some other pair of vectors. Okay? So A of Z2 A applied to, I just mean by this, applying A to all the different basis vector, all the different points in Z2 results in an oblique lattice L. Okay? And L is just a combination, the points in L are combinations of the basis vectors k1 times v1 plus k2 times v2, where k1 and k2 are integers. And here v1, say, is a of e1, and v2 is a of e2. Okay? Stay with me. Stay with me. Okay, now, I want to introduce one more geometric, actually there are a couple other things I have to introduce. It's very common, matter of fact, crystallographers do this. Do we have anybody who's actually done any crystallography in here? By the way, I'm just curious. And this is all new, all right? But if you do any kind of imaging, you know, you're going to see these terms and see these ideas, all right? Especially these days in molecular imaging and things like that, where these things are coming in really interesting ways. As a quick geometric description, so to jump ahead a little bit, now I'm going to come back to this in a second. Crystals come into this because you consider crystals to be modeled on lattices, all right, where there's an atom at each lattice point, all right? And of course, the idea of considering oblique lattices is because some crystals are modeled on a rectangular lattice or a cubic lattice, but a lot of crystals aren't. I mean, they're shear, they're oblique, all right? There's a geometric, just to get an idea of somehow, just to attach a number that describes the lattice in some loose but helpful sense, you often talk about the area of the lattice. So you often speak of the area of really what's called a fundamental cell or fundamental parallelogram, fundamental cell in the lattice. And that's just the area of one of the parallelograms spanned by the basis vectors. All right? So again, if here's the lattice, and say this is V1, V1 and V2, then the area of the lattice is the area of the, we're going to come back, we're going to need this formula, we're going to need this concept in just a second. The area, you talk about the area of the lattice is just the area of the parallelogram determined by the basis vectors. So the area of L is area of the parallelogram. All right, and the reason why crystallographers think about that is because they think of sort of that as a fundamental cell or fundamental building block for the rest of the crystal. That region in space is the fundamental building block for the rest of the crystal, and the question is, how big is that? You know, so they talk about the volume of the fundamental cell. Everything in crystallography, of course, is really in 3 dimensions. I'm only doing things in 2 dimensions. So I'm talking about the area in terms of volume, but that's what they do. They talk in those terms. All right, so the area of the integer lattice is 1, all right, because each one of these basis vectors is length 1, and they're perpendicular. The area of that square is just 1. All right, now, so I wanted to introduce that. But the real thing I want to get to, of course, is what happens if we consider the Shaw function for an oblique lattice and what is its Fourier transform. So again, considering the Shaw function for an oblique lattice is like considering a model for a crystal where the underlying lattice structure, or underlying crystal structure, is on an oblique lattice instead of on a square lattice. So we can consider, let's call it the Shaw function of the lattice L. I'm struggling here with my script letters. X. So let me just write it like this. It's the sum over all points in the lattice. So those are all the vertex points, all the lattice points, the grid points. I put a delta at each one of those points, say delta of x minus p. All right? You put a delta function at each lattice point p. Okay, now, the real question is, what is the Fourier transform? What happens to the Fourier transform? All right, what is the Fourier transform of the Shaw function associated with an oblique lattice? Lots going on here, right? I mean, you have to have the notion of a lattice. You have to have the notion of an oblique lattice. You have to have the notion of a Shaw function on the lattice. And now you're asking about the Fourier transform. I mean, what levels of complexity have been added to this simple conversation? All right. And the reason why, and again, I'll come back to this in a second, but the reason why you want to know about the Fourier transform is because in honest-to-God scientific experiments on crystallography, when you're shining X-rays through a crystal, you get a bunch of spots. And the spots, the pattern of the spots is determined by the Fourier transform of the crystal that's doing the diffracting. All right, so if the crystal that's doing the diffracting is modeled by the Shaw function for a lattice, what you want to know about is you want to know about the Fourier transform of that Shaw function for the lattice because that's what you're seeing. All right, those are the spots that you're seeing. Okay, now, finally, here's where this reciprocal relationship comes in. And it's just great. And again, unfortunately, and I really do feel badly about this, I don't have the time to really talk too much about the motivation for this or even derive many of the formulas. So I just want to show you, in some sense, what the punchline is without the whole setup. And it just kills me, but I've got to. All right. So here is, I'm going to put two other lattices on that board, but here's the integer lattice. All right. Integer lattice. Okay, Z2. All right, I have two linear transformations. I have my linear transformation A that's going to go down to the oblique lattice L. That's the sort of the lattice that I'm starting with. Here's the oblique lattice L. All right, L. All right. And then the crystallographers, and even mathematicians too, but for completely different reasons as far as I can tell, define what they call the dual or reciprocal lattice, L star. So L is A of Z2. L is the transformation A. Any lattice can be realized as a linear transformation applied to the integer lattice. So L is A applied to Z2. All right. Then the crystallographers define the reciprocal or dual lattice to be, guess what? A inverse transpose applied to Z2. All right. So they take A inverse transpose, take everybody's attention. Would you like to hear it again? No. A inverse transpose. Now that's also another linear transformation, so it goes into another lattice, all right? And I don't have great confidence in actually how I draw it, but something like this, say. All right, L star. And they call that the reciprocal lattice. And in fact, as you can easily check, the area of L star, that is to say, the area of one of these fundamental polygons, polyhedra is, so I certainly didn't draw it very well because it doesn't look quite so easy, is the reciprocal of the area of the other lattice. Now, this is one definition of it, and this is the cleanest definition. It's completely unmotivated. I'm sorry. There are different ways of motivating it. There's one discussion in the notes. That is, it's completely unmotivated definition. Why the hell would you define the dual lattice or reciprocal lattice this way? You just have to take my word for it, or look around for other motivations for it, other definitions for it. And in fact, people who work in materials and people who work in crystallography actually have a geometric construction of the dual lattice. Given a lattice L, they have a way of constructing geometrically the dual lattice, like a ruler and compass construction. All right, so it's a time-honored, important construction in materials to pass from a lattice to the reciprocal lattice. Now, why? What is the big deal? Because the fundamental fact on the Shaw function is that the Fourier transform of the Shaw function for a lattice is the Shaw function for the dual lattice, except scaled by the area. So that's the fundamental fact. Is that the Fourier transform, I got too many F's and L's and everything else in here. The Fourier transform of the Shaw function of the lattice L it's a beautiful formula. It's 1 over the area of L, all right, times the Shaw function of the dual lattice. Now again, in higher dimensions, which is where the real applications of crystallography go, you'd have the same result except you'd have volume here instead of area. All right, but it's the same kind of result. And the definition of the dual lattice is the same, except instead of a transformation in R2, instead of everything happening in R2 here, everything would be happening in R3. You'd have the lattice of integer points in R3. You'd have a 3 by 3 matrix going over to an oblique lattice here in R3. You'd have the inverse transpose going into another oblique lattice in R3, and so on. All right, and you have the same result. All right, this is exactly, if you believe it, analogous to the one-dimensional formula. All right, this is the analog of the one-dimensional formula. This is the analog to the Fourier transform of the Shaw function with spacing. The one-dimensional Shaw function with spacing p is 1 over p times the Shaw function with spacing 1 over p. All right. There, reciprocal just means 1 over. But see, the thing is, you miss something. All right. If you just look at that, or you either miss something in the one-dimensional case, or something new and deeper is revealed in the higher dimensional case. Because in the one-dimensional case, reciprocal means reciprocal. All right, it just means 1 over. In the higher dimensional case, reciprocal means inverse transpose. All right, that's the change in point of view. That's sort of the change in intuition, and it's very important. All right, that's something you don't see in the one-dimensional case. All right, that's a difference between the one-dimensional case and the two-dimensional case in how to understand the notion of reciprocity, in how to understand what reciprocal means. It's a mathematical fact, and not only a mathematical fact, a fact of nature, that in higher dimensions, reciprocal often can be interpreted as involves, ergo, ipso, fitip, blah, 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 reciprocal transpose. All right, now, so what about crystals and all this? I made allusions to this a lot, so let me just say quickly what the situation is for crystals and why this is so important, or where this comes up. So again, for crystals, all right, so again, when we did this in the one-dimensional case, the idea is you study a crystal by studying the electron density distribution of a crystal. What is the electron density distribution of a crystal? you conjecture, you measure how the electrons are distributed about an atom, and then you periodize that. Crystals have a periodic structure, all right? So rho of x in 2 dimensions now is the density, electron density for an atom in a crystal. All right? The electron density distribution for the whole crystal is a periodized version of that. For the crystal as a whole, you take a periodized version. That's the whole point about crystals, is they have periodic structure. How do you take a periodized version? You convolve with the appropriate Shaw function. All right? So if this is the crystal whose atoms are, which you model as a bunch of atoms at lattice points, that's L, then the density for the lattice, the density for the crystal, is the density for a single atom convolved with the Shaw function of L. All right? That's sum over all the points in the lattice of rho of x minus p. Same as in the one-dimensional case. All right, so if the density looks like that there, then that pattern is just repeated for the whole lattice. And I can't draw this too well, but you get the picture. All right? This is now periodic with respect to the lattice. This is also a different phenomenon. It has 2 periods. All right, it's periodic in that direction and periodic in that direction. All right, it's periodic on the whole lattice. The pattern repeats on the whole lattice. Now, X-ray crystal experiments, X-ray diffraction experiments measure the Fourier transform. All right, that is, an X-ray diffraction experiment produces the magnitude of the Fourier transform, but just basically think of it as the Fourier transform, produces the Fourier transform of rho. Fourier transform of rho of the lattice. Okay? That's what it does. You see a bunch of spots. What you're seeing is the Fourier transform of the lattice. And what is that? Well, that's the Fourier transform of the convolution. So that's the product of the Fourier transform of rho with the Fourier transform of the Shaw. So this is the Fourier transform of rho times the Fourier transform of the Shaw function of the lattice. All right, but we know what that is. It's the dual lattice. That is, this is the Fourier transform of rho times 1 over the area of L times the Shaw function of the dual lattice. Okay? And if I take the product of a function times a bunch of delta functions, what do I get? I get sum over the points, let me call it P star in the dual lattice. All right, they're just delta functions at the lattice points of the dual lattice of the Fourier transform of rho at, I don't know, S times delta of S minus P star. Okay? It's the Fourier transform of the density function times the sum of deltas. And remember what happens when you take a function times delta, it just pulls out the value. Oh, sorry. P star. Okay? Okay. So once again, you do your experiment, and unless you know the math, you're not going to be able to draw the right conclusion. You might think that you pass a bunch of X-rays through the crystal, and the spacing of the lattice points that you're seeing should be proportional to the spacing of the lattice points in the crystal, but it's not. All right? Nature, for whatever mysterious reason, is taking a Fourier transform. All right? X-ray crystallography, X-ray diffraction takes a Fourier transform for you physically. All right? It's kind of spooky. All right? And what you're seeing is you're seeing the points at points, you're seeing those little spots that appear on your X-ray film at points on the dual lattice. All right? And unless you know the math, unless you know that in higher dimensions reciprocal means inverse transpose and so on, they say you can kiss your Nobel Prize goodbye. Right? But if you sort of follow your pencil through this and see how the math plays out here, you can draw conclusions about the crystal by knowing this. Okay? I think it's really cool. I think it's a really interesting application and physical manifestation of this fact that in higher dimensions, inverse transpose means reciprocal. All right, and I should say, by the way, so I don't have time to derive this formula. I'm sorry for that. The derivation of this formula, and that shouldn't surprise you given how all these terms are coming in, involves exactly the generalized stretch theorem. All right. The reason why inverse transpose comes in here and the reason why the dual lattice comes in is because in deriving this formula it uses exactly the generalized stretch theorem. All right. That's how it comes into it in deriving that formula. Okay. Isn't that nice? So I say I wish we had one additional day because I would like to go into a little bit more detail about this, but we don't. We don't because I spent all that time on the damn fast Fourier transform. Everybody wanted to see that damn fast Fourier transform. All right, now, so full stop. Speaking about things I can't spend enough time on, there's one more topic I won't be able to spend enough time on. All right, the final topic in the class is application of the two-dimensional Fourier transform to the problems of medical imaging, and particularly the problems of tomography. So, leave this fascinating subject behind and pass to another fascinating subject. I'll start it off today and then we'll finish it up next time. All right. So the final application is, final topic, is the application of the two-dimensional Fourier transform, 2D Fourier transform, to medical imaging. And in particular, the problem of tomography. I will tell you what the problem of tomography is in just a second. The problem of tomography, fundamental problem of tomography. Now, let me say at once that what I'm going to be looking at is really in the realm of computer tomography, all right, of tomography, not MRI, all right. But as it turns out, this is not MRI. All right. As I say in the biz, the modalities of imaging for the two kinds of two approaches are different. However, it's also true, for whatever reason, well, for a reason that we can't really get into, that the final formula that I'm going to get to solve the problem of tomography is the same as the formula you get when you're using an MR system, all right, to do the imaging. All right. So what we're doing here, although it's in the realm of tomography, CAT scans and things like that, actually the final formulas that you get and a lot of the considerations that we're going to talk about actually apply in the MR case, magnetic resonance case, NMR case, nuclear magnetic resonance. But again, I cannot get into it. All right, here's the setup. Here is the basic setup. All right. You have a 2D region, two-dimensional region. Think of as a slice of your body filled with goop. Blood, bones, organs, you know. There you are, all right? And there's all that goop inside you, all right? And that goop inside you is described by a function of variable density. You can imagine describing the density of the goop. All right? So describe the goop by a function mu of x1, x2. All right? So this is taking place, say, in the x1, x2 plane, and mu gives the density of the goop at each point. x1, x2 at each point. All right? So if you know mu, you know u, so to speak. That is to say, you want to get mu by taking measurements. you want to recover mu x1, x2 by X-ray measurements. Or just let me just say by whatever. All right, that's what you want. You want to reconstruct the function mu. Okay, now, here's how it's done in tomography. All right, the approach to tomography is the following. Tomography means, if I get this right, I forgot to look it up to get the precise, I think it means section. All right, so the idea is you're taking sections, and particularly actually what I'm going to do is I'm going to take a one-dimensional section. That is to say, I'm going to pass a line through this region. So the approach via tomography, a line meaning I'm going to pass an X-ray. Approach via tomography is you shoot an X-ray through the region along a line. Okay? And it comes out the other end. It gets diffracted, it gets attenuated by all this goop in the middle. All right? So here's the X-ray. And there's a lot of stuff in here. And you measure what happens to it when it comes out. So you know you know what it was going in, and you measure what it is coming out. So you know, say it goes this way. All right? So you know the intensity of the X-ray going in. All right? And then it gets attenuated, so you measure the intensity, so let's call this I naught. The initial intensity. All right? You measure the intensity going out on the other end. Let's call that I. All right? Now, then, it is not hard to show as a reasonable approximation, and again, this is derived in the notes, you can show that there's a relatively simple, we'll see. There's a relationship between the intensity going out and the intensity coming in. So this is I naught going in, I coming out. And it's attenuated, it drops exponentially, and it's given by intensity coming out is the intensity going in, and then I say it drops exponentially. How? It drops exponentially according to the integral of mu along the line, sort of like the average density. All right, mu is a variable density. But the total drop in intensity is given by e to the minus integral. So integral of L over mu, I'm using a shorthand notation here, is the line integral of mu along L. All right? So again, you can sort of think of that as the average density or whatever. There are different ways of making that argument. And again, I don't want to take the time now to try to derive that formula for you. But it's actually not that hard to derive. And it's not even that hard to believe. Okay, now, again, you know I naught, you measure I. All right, so all those numbers are known. What you don't know is you don't know mu. And in particular, you don't know the integral of mu along a line. Now, what you do is you make lots of measurements. You send X-rays through along all different lines or along whole families of lines. You send X-rays through along many lines. All right? This way, this way. And usually you think of them as parallel lines, but then you change the angle. You send them in this way. You send them in this way. Don't think of this as a lattice. I'm just changing my X-rays. All right, so you send a bunch of lines in. All right, then you know, and you measure at every time, you know the intensity going in. You measure the intensity coming out. So that means you know the integral along all those different lines of mu. So once again, you write this down. I equals I naught e to the minus integral of mu over the line L, all right, for all different L. All right, you know this, you measure this, so then you know all the numbers integral over L of mu. When I say all the numbers, you know them along all these different lines because you make those measurements. All right? And the fundamental problem of tomography, as it is often stated, is can you recover mu by knowing all these line integrals? That's the problem. So again, I'll make sure you understand here that at least what you know and what you're trying to figure out. All right, you know the value of these integrals because you know this formula. All right, and you know the intensity going in, and you measure the intensity coming out. So that tells you what this is. You just solve for it, a log, in terms of logs. All right. So the question is, the fundamental problem of tomography is can you recover mu by knowing the integral of mu along L for all L, for all lines L? That's the question. And the answer is affirmative. The answer is in the affirmative. The answer is yes, and involves the two-dimensional Fourier transform. That's how it comes into the picture. Now, I'm not going to get to that today, but I'll tell you how we're going to approach it, actually. So the answer is yes. It's not obvious, all right? And it's certainly not obvious that the Fourier transform is going to come into this in any sort of way. But here's the approach. This is the approach that we're going to take, and here's how it works. And I say it's not obvious. It was a brilliant idea. All right. You consider these numbers as defining a transform of mu. All right. And what I mean by that is you start with a line. What's it a function of? It depends on the line. The number depends on the line. All right? So starting with a line L, you compute the number, the integral of mu along L. L goes to, that's a line, goes to the integral over L of mu. That's a number. All right? And when I say transform, what I mean is you consider this a transform of mu evaluated on the line L. Now that's sort of mind expanding for you, but that's the way you look at it. That is, write this as R of mu, the transform of mu at a particular line. So again, that is by definition that integral. That's the integral along L of mu. All right? That's called the Radon transform of mu. We're almost out of here. That's called the Radon transform of mu. And the fundamental problem of tomography can be stated as saying, can you invert the Radon transform? R of mu gives you something you evaluate on L. The question is, can you find mu given all the values of R of mu? Can we invert? Is there an inverse Radon transform? To find mu. And the answer is yes, and the answer is in terms of the two-dimensional Fourier transform. It's amazing. All right? It's just amazing. But that's what's going to happen. So that's why the two-dimensional Fourier transform, that's why Fourier transform techniques come into medical imaging, because of this connection, because of exactly this connection. Okay? So we will finish up with that next time. And I'm going to go take a pill and collapse. Thank you all. I'll see you all on Friday.